Uh, yes. So welcome everyone to the next N3AS seminar. And today we will have Professor Timothy Tait from University of California, Irvine, talking about early period of QCD confinement. So please go ahead.
Thank you very much. It's very nice to be here and also to see some old friends and also make some new ones. So I'm going to talk today about some work I've done recently that has to do with an early period of QCD confinement. I have to apologize. It doesn't really have any neutrinos in it. It has maybe a wisp of nuclear astrophysics. It does have some symmetries though, so hopefully it'll be interesting. Also, because it's a topic I've been working on for a few years, and here's an outline of what I'm going to talk about, starting with some motivation and then talking about the meat of sort of the subject itself, and then a few applications. I'm going to go through the applications very quickly, and I have slides that I'm not going to go through properly with the idea that I'd rather sort of give you a broad overview, and then you can always ask me questions. I'd be happy to fill in some of the details. And that way, at least the slides are there so that you can see them. So the invitation or the motivation for what I'd like to talk about today is basically exploring how beyond the standard model physics could impact early cosmology. So of course, we're all familiar with the phases we think the universe went through along the lines of getting to where we are today. And of course, we know quite a bit experimentally about the late phases, the CMB, even Big Bang nucleosynthesis is actually, a fabulous constraint on anything that we do to physics beyond the standard model that would impact the universe after a few MeV or so. And then earlier we have some extrapolations from the standard model, like the fact that we think that QCD went through a phase transition at around a GeV scale, where it went from the description today in terms of hadrons and mesons into one of free pions and gluons. At an even earlier time, the standard model predicts that we should go through an electroweak phase transition in which the Higgs BeV switches off, and at higher temperatures, we have no explicit masses for the particles. And then there are also some things that we think may have happened, but we are not as sure about them. They're not really extrapolations of the standard model. They're actually extrapolations for guesses of how to extend the standard model. So we know at some point we had to introduce an asymmetry between quarks and antiquarks, so baryogenesis. That might have happened around the electroweak scale, or it might have happened much earlier. Of course, there are even some theories where it might have happened later. And the dark matter, if it froze out, should have happened sometime around a few GeV if it's a WIMP. And of course, that also could have happened at a different time, or the dark matter could have been produced through a different process. And the main thing here is that at these early times before BBN, most of what we know about the physics of the early universe is an extrapolation, which is based on the standard model plus ingredients we know should be there, like, for example, dark matter. And in this talk, I'm going to explore the idea that the QCD phase transition initially happened at a much higher temperature than GeV. So if I use the sort of language of ancient cartography, at early times, here there be dragons. And of course, there's another dragon that we've all been dealing with for quite some time now, but luckily we seem to be learning how to actually deal with this one now. So the motivation is I'd like to learn about fundamental physics from early cosmological probes, like, for example, the abundances of dark matter or baryons. And then, of course, knowledge of the cosmological history of the universe is essential because it determines how those processes take place. It is the stage at which all of our acts in our play are happening. A non-standard picture, even at early times, could distort how we interpret those observations, and they might point us towards theories that are not actually the ones realized in nature, just because we're making an extrapolation of what the cosmology is doing, which is not anchored firmly to data. And so what I realized at some point a few years ago is that I really wanted to have some better understanding of the space of possibilities so I could put those types of effects into context. And the one I'm talking about today is really a very old idea, which is that the coupling constants, which of course are not constant anyway, of the standard model, could take different values at different times. This is a very familiar idea. We have very good indications from those late time measurements that any such evolution must have been very, very slow and maybe not happening at all. And that's based on a variety of measurements. But of course, at times before BBN, there's still some room for a theoretical physicist like myself to play. So I'm going to focus on the somewhat radical idea that QCD had such a different coupling at some early epoch that it actually confined at some time with a much larger confinement scale than the value around a GeV of the standard model. And everything I'm going to say is going to be, fairly imprecise in the sense of theoretical physics. So when I say GeV, I really mean the 350 or so MeV that you would find as a typical value of QCD today. And I'm going to be talking about radically different values that could be as high as like a TeV or so. And of course, to do that, to make it happen realistically, sometime before we actually get to Big Bang nucleosynthesis, we have to relax back to something that looks like the standard model with the lambda that we measure today. So just to make it really clear, I am really talking about the SU3 color interaction of the standard model, and I'm going to play with it at early times, but I do realize it has to go back to normal today. Believe it or not, I've had referee reports where people somehow didn't quite actually track all of those caveats. Of course, I'm doing something dramatic. I'm trying to make a big change in the coupling. More modest modifications are also interesting, and they could even be considered more likely, and you can find some investigations of those too. So why do I jump to the dramatic case? Well, because it actually does seem to help recast some old problems in new light, and therefore I get some progress in terms of connecting with BSM physics that's interesting. And also it's actually a lot of fun because we get to do things like reimagine chiral perturbation theory if the QCD scale had been a TeV, but most of the standard model looked more or less the way it does. We can play similar games actually with the other interactions. For example, I could ask SU2 weak to confine at some time before it ultimately gets broken at the electroweak phase transition. And that gives me an even weirder universe than the one I'm going to describe. And this has actually been investigated by a few authors here. And actually some applications to dark matter freeze out are coming from myself and some collaborators soon, like maybe within the next week or so if all goes well. So let me say a little bit about a period of early confinement. Also, I should mention, just by way of process, that I'm not offended if people want to jump in and ask questions, but I won't be able to juggle looking at the chat or anything, so you'll have to actually get my attention if you want to do that. So what I'm going to do is introduce dynamics that promote the strong coupling of the standard model, the strong SU3 coupling, to a dynamical object. And so I usually am going to denote that by phi, but on a few places where I was working with different collaborators, it may be called S for singlet. And so the idea is that if there is some scalar field, which is a standard model singlet, that couples to the gluon kinetic term in the following way, then it actually modifies the coupling effectively, right? And the idea is that because of gauge invariance, actually the coefficient of the gluon kinetic term is everything there is to know about the coupling of gluons to the standard model through the usual covariant derivatives. And so therefore, if I give a vacuum expectation value to this field phi, I change that coefficient, and effectively I end up with a different coupling that's been modified by something that depends on what I thought the original coupling was, and also what that vacuum expectation value is. And this is something that we introduced in our context, though I mean, other people had also looked at this type of thing before, with Tait Epoch in this reference. So of course, if I want to connect with something like a more fundamental theory, phi could be something like a dilaton or a radion in a theory with extra dimensions. It could also just be some ordinary four-dimensional field that has a coupling induced radiatively. So maybe phi couples to some vector-like quarks, which then have their own, usual covariant derivatives to couple to gluons, such that there's an effective coupling. And actually, another thing that you may have noticed is that my phi field actually looks like the Higgs at low energies in the standard model. The Higgs is also produced from two gluons through an operator that looks identical to the one I'm starting with. And so the Higgs is even an example of this, but it has an effect that's much smaller than the one that I'm interested in. And so that's why I'm going to something beyond the standard model. So this coupling G0 is just the strong coupling in the absence of any VEV. If I think that I normalize things such that the phi VEV being 0 is the standard model, then it's just the standard model QCD coupling, and it runs just like an ordinary QCD. So in particular, at one loop, I can write down what that looks like in terms of the contribution from the gluons and also from the quarks. So this is written in terms of the number of flavors. And of course, that's a log of evolution. And then the effective coupling also just has this tree level piece, which looks like the VEV of phi over the strength of that interaction, which I've written as M star. So now, based on this new value of the coupling, I can estimate the scale at which QCD gets strong, and we expect confinement to take place. And that, of course, is exponentially sensitive to the VEV of phi, just like it was exponentially sensitive to the boundary conditions in the standard model. And so I'm going to parameterize this as a parameter I call XC, which multiplies lambda 0. So lambda 0 is the coupling, the QCD confinement scale in the standard model, so that's still about 1 GeV scale. And then C is the amount that I can actually push that up by playing with the VEV of phi. And if I have 6 massless flavors, right, which I do at very high temperatures in the standard model, if I want to get confinement at TeV, then what I need is that the VEV of this phi normalized by that coupling strength M star should be about minus 0.8 or so. So this is getting to the edge of the limit of the applicability of the effective field theory I've used to write down my coupling of phi to gluons, but it's actually in the range where it's still valid. If it were induced radiatively, it would require me to have about 10 vector-like quarks at the mass scale of M star, which is a lot. But on the other hand, it's still something that could be saved from the LHC if the scale M star was a few TeV, such that the LHC would not really be producing these things appreciably. This plot just basically shows the evolution of the strong coupling as a function of temperature, with the idea that as I change the VEV of phi, which is written here as V sub s, from different values, at 0, I get something like standard model confinement happening around a temperature of a GeV. And as I go to more negative values for the VEV of phi, I get actually confinement at an earlier time. And you can see how I can even get up to a TeV if I push it to about 0.8, minus 0.8 or so. The phase of phi's VEV is actually physical, right? And that should be clear from the original. Oops. Oh no. How do I go back? Okay. Which you'd think I'd be able to do this after giving Zoom seminars for 2 years. But anyway, it's clear that the phase is actually relevant because it plays off against the underlying normalization of the kinetic term. And the theory is well defined as long as this thing in parentheses is positive. If it were negative, I would start to have ghosts. So I need to engineer a potential for phi that has temperature dependent corrections such that the VEV of phi shifts, moving from some value at high temperatures, which corresponds to a large lambda, to a value at low temperatures that matches on to the lambda we see at low temperatures today. And so this was also something that we explored. So initially there's some VEV for phi that gives us a lambda around a TeV. And then the phi potential is such that as I go to lower temperatures, eventually it shifts to another value such that lambda is around GeV. And I have actually a few slides in the backup that have some ideas for how that can happen. We do have fully fleshed out theories, but what I really wanted to tell you about was more like the phenomena that are actually produced by this type of effect. So I'm not going to actually go into those in detail. I'm just going to ask you to take on faith that I can construct such a potential. And again, if you ask me, I can show you one. So the first, right, the original QCD phase transition, the one that happens around the TeV scale, takes place at very high temperatures. Let's imagine that this is before the electroweak symmetry is broken, and therefore the standard model quarks are massless at this point. For 6 massless flavors, the phase transition is expected to be a first order phase transition. This is due to some old arguments by Pozharsky and Wilczek. This diagram is actually just from a review of ordinary QCD in the standard model, and it just shows the dependence on the up and down masses that are taken to be equal. That's on the x-axis. On the y-axis, we have the strange quark mass. The physical point here is the red oval. And you see the phase diagram, which has actually first order phase transitions, both when all the quarks are massless. So that's the one that's kind of most like having 6 massless flavors, though this plot is for 3. And also actually for pure glue, when all the quark masses go to infinity. So with this first order phase transition, the confined vacuum forms actually via bubble nucleation. It's like some of the ideas we have for the electroweak phase transition and theories beyond the standard model. And it's very interesting actually, because after confinement, chiral symmetry breaking, right, the condensate of Q bar Q, also breaks the electroweak symmetry, and the condensate acts as a tadpole for the Higgs and therefore induces a VEV for it. So this is actually a realization of technicolor at high temperatures, where the electroweak symmetry is broken by actually a condensate of the quarks. In fact, it's old school technicolor, not the more modern technicolor that existed for much longer, though was eventually ruled out as the entirety of electroweak symmetry breaking by the LHC. So schematically, at the critical temperature, something like this happens. In most of the universe, we're living in the free phase, where quarks and gluons are running around happily and unconfined. There's no chiral condensate, Q bar is equal to 0. There's no Higgs VEV either. And then since I'm at the critical temperature, at some point, we tunnel through a barrier in the potential for Q bar Q, or we start to confine, in other words. And then we form a bubble of the confined vacuum. Inside the confined vacuum, the quarks and gluons are bound into hadrons and mesons. Mesons and baryons, I should have said. There is chiral symmetry breaking, which is of order lambda cubed. And the Higgs Vev is non-zero because this thing looks like a tadpole for it. And you can do a lot actually to try to understand the physics of what the universe would look like in this confined phase. The important active degrees of freedom are the lightest hadrons. They are the around 35, right? Because there are 6 flavors, pseudo Nambu-Goldstone bosons. Their properties can be described by chiral perturbation theory using the same machinery that we use to do chiral perturbation theory at 0 temperature, to talk about the actual pions that we see. And so what we do is we write down a chiral Lagrangian that's invariant under the SU6 cross SU6 flavor symmetry. We match the parameters in it so that we produce the low energy QCD data, but then we scale up the dimensionful quantities to the high scale confinement scale. So for example, the mass term for the pions has a coefficient that I've written as kappa here, right? Remember, U is an exponential of the pions and MQ is the quark masses. So the coefficient there can be matched to low energy QCD, but then this gets scaled up by 3 powers of C because it's a dimension 3 parameter. And the K constant for the pions is again scaled up from the 94 MeV that's familiar at low energies. And if I put all these things together, then the pion masses actually get scaled up by 1 power of C. And also remember, the Higgs Vev is taking a non-standard and non-zero value actually in this period. And so there's also a factor of that. So the thermal corrections to the Higgs potential are dominated by top flavored and sometimes bottom flavored mesons rather than the top and bottom quarks. The fact that they're bosons means that the thermal corrections are somewhat different. And also actually the way the Higgs acquires the Vev is somewhat different. It's also a first order phase transition. And what we plotted here is for a couple different values of the high scale confinement scale, either 200 GeV or 400 GeV, we plotted the value of the Higgs Vev as a function of temperature. So the universe is cooling down, we're coming in from the right here. And for the high confinement scale, at some point we confine, the Higgs Vev gets jacked up to a value much larger than in the standard model. And then of course, eventually things go back to normal. When QCD goes back to normal, so does the Higgs Vev. And something similar happens for a smaller value of C at a later time. You can compute the spectrum of pions. The pion masses range from around 10 GeV up to about a TeV for these 2 choices of lambda QCD. And you can also see this fact that the chiral condensate acts as a tadpole for the Higgs. There's actually no new parameter to describe that. The quark masses, which we think of in chiral perturbation theory and QCD is just static quantities, are actually dependent on the Higgs Vev. And you can see the tadpole for the Higgs comes out from that same term. So the pion mass term we're familiar with is here, but there's also actually a term that is linear in the Higgs and acts like a tadpole for it. So I want to say a little bit about a couple of applications. And so the first one is we can actually realize a model of spontaneous baryogenesis using this kind of construction. So famously, the standard model does not have enough CP violation in the CKM phase to generate a sufficient baryon asymmetry. That's one of the many ways in which the standard model fails to satisfy the Sakharov conditions and generate a baryon asymmetry. So one interesting idea is actually to invoke the strong CP phase as a source of CP violation. So the idea is I'm going to write down some coefficient for GG dual, which is usually called theta bar, right? Theta bar is related to some underlying parameter plus the argument of the determinant of the quark mass matrix. And of course, in general, we know from experiment that theta bar today is very tiny because we can't measure a neutron electric dipole moment. But if there's a dynamical solution to the strong CP problem, such as the axion, this effective phase could itself be a dynamical quantity and could be different in the early universe before the axion reaches the minimum of its potential. So in other words, there may be another dynamically evolving thing. The axion, of course, its evolution is also governed by QCD. That'll be the last thing I sort of briefly touch on. So in some sense, the axion is just actually another example of a way in which you imagine that the properties of the strong nuclear force are different in the early universe than they are today for a dynamical reason. And it was realized actually in the 1990s that the rolling of the axion to its minimum also provides an out of equilibrium condition, which is one of the 3 conditions enumerated by Sakharov that are necessary to produce a net baryon asymmetry from a universe that starts out symmetrically. So The challenge to realizing this idea, however, is that the baryon number violation itself comes from the electroweak instantons. They're active above the electroweak phase transition. So once the Higgs gets a VEV, the sphalerons are very highly suppressed. And so there's a big change in their behavior. But of course, the axion starts rolling when its mass turns on, and that's around the QCD scale. And so there's a mismatch between where I have the baryon number violation I need and where I have the out of equilibrium condition that I need. And it's fair to say that actually these authors did actually address this challenge by invoking some new physics of their own. But I've already sort of anticipated what's going to happen here. If I can raise the QCD scale, the axion will start rolling at a much earlier time. And if that's actually above the electroweak phase transition, then it'll happen at the same time as the sphalerons are active. And of course, because I'm also turning on a Higgs VEV, once the QCD phase transition turns on, the sphalerons themselves will get damped, and so that will happen at an earlier time. But the point is you have everything happening right at the same scale, and so you have all the ingredients active in the same period of the universe. And so you can imagine that it'll be easier to realize a baryon asymmetry if I do that. Now, this is one of the places where, because of the time, I'm not going to go through the calculation in great detail, but I do have the slides here. And just to sort of very quickly cartoon what happens, if there is some non-zero CP violating phase in the strong sector, it acts as a source for GG dual. And that in itself actually looks like a source for WW dual. And that's because you could imagine the easiest way to explain this is to look at the low energy theory and to realize the eta prime interacts both with GG dual on one side and WW dual on the other. Now, of course, we're not precisely in the confined phase, and so it would probably be better to think of this as actually a loop of quarks that have the same quantum numbers as the eta prime. And of course, that exists too. So then using chiral perturbation theory, we can actually estimate how large the bridge between GG dual and WW dual is. And the point is that the weak WW dual is actually equal to the divergence of the baryon current, and therefore it looks actually like a chemical potential for baryons. So that might not have been totally comprehensible, and I apologize, I went through it really quickly. But the point is that there's a chemical potential for baryons that has to do with the axion rolling to its minimum. And then we can estimate the amount of baryon production given the sphalerons as the rate for which baryon number is violated. So putting this all together and putting in estimates for the sphalerons rate and also for how the axion mass, right, which is necessary to know how fast it's rolling, we can actually estimate the resulting baryon asymmetry to be something like 10 to the minus 11, the initial displacement of the CP violating phase from 0, from the value it settles on to today. And then there are some ratios. There's the ratio of the Higgs VEV during the early confinement to the value of the early confinement. And then there's a ratio of the temperature at which the sphalerons switch off to the reheat temperature. And this was an important thing actually in the Cosmological et al. Construction, but it's actually not very important here because here everything's happening at the same temperature. And so this ratio is very close to 1. So this is actually sort of surprisingly independent of all the new physics parameters. And that's largely just because everything is kind of canceled out in the ratios, and a lot of the underlying numbers are actually fixed by low energy chiral perturbation theory. The number it gets is maybe a little bit on the low side, given that sine theta bar can't be larger than 1. We'd be more comfortable if this was 10 to the minus 10. But you can actually find models where you realize a Higgs VEV that is bigger than the early confinement scale, and you can actually make this work if you play with the potential of the phi field a little bit. And so this actually works like a theory that kind of naturally produces something that is maybe not exactly the baryon asymmetry we see today, but it's within a factor of 10 of it, and with some knobs that I can adjust to get there. So that's actually very amusing, and definitely suggests that I have sort of accomplished what I set out to do, which was to try to recast an old problem, right? The problem of how I generate a baryon asymmetry in the context of a universe that has a non-standard cosmology where QCD confines at an early time. So before wrapping up and talking about phenomenology and asking for some questions, I'll say a little bit about a couple other applications that we've played with. So one is to WIMP freeze out. So if I imagine that there is a dark matter particle that is a weakly interacting massive particle, let's just say for argument's sake, it's a standard model singlet, it's a Dirac fermion, and it likes to interact with standard model quarks. So all of those are, of course, model dependent choices that I'm choosing to make here. But so the idea is you can imagine that there is a coupling of the WIMP to the quarks, and this matrix in flavor space, I'm just going to set it to the diagonal, proportional to the quark-Yukawa coupling. So the up quark Yukawa has been taken out as normalization. And so basically, I'm assuming something like minimal flavor violation, where the coupling of the dark matter goes like the quark mass. And that's to prevent large corrections to flavor observables that would probably be ruled out and require this, this coupling to be very tiny. So now if I imagine that the dark matter is freezing out during the time that QCD is confined, I can actually turn this into, again, the chiral perturbation theory. It turns out that this operator, from the point of view of the quarks, is just the same operator that gave the pions their mass. So I already know how to deal with this coefficient, and it determines how the dark matter interacts, therefore, with the pions, which again are living as an exponential in the U field. And then the couplings beta are here. So we can imagine that this actually might even be the kind of interaction the singlet phi that I introduced in the first place would mediate if it has some mixing with the Higgs and couples to the dark matter. So continuing to turn the crank, what I find from this interaction is two interesting things. One is that the mass of the dark matter actually gets shifted by some amount. It's a signed quantity. It can be shifted either in a positive or negative direction. And that's just the natural consequence of dark matter coupling to quarks and the fact that there is a chiral condensate. Again, this is something that's more generically true in many theories, but it's often negligible, and so we just don't talk about it very much. And then, of course, there are interactions that look like two dark particles interacting with two pions. So both of these are pretty interesting. They tell you that at the time of freeze out, the dark matter may have a different mass than it does today, and also that it may annihilate into pions, which changes the case from when it's annihilating into quarks. And so, moving forward through the calculation of the relic abundance of this dark matter chi field, I can actually compute the cross section so that the solid lines here represent two different choices, the blue and the green, for that interaction strength with the quarks. So for larger values of MS, I'm making the interaction strength smaller. Therefore, the cross section is smaller. And you can also see there's a threshold here at the top quark mass, because the top quark obviously has a stronger interaction, given that the interaction is assumed to scale with mass. So the standard model case is the solid lines. And then when I go to this early confined case, the annihilation into pions is actually quite a bit larger, and that's because it's enhanced by the confinement scale. So I can then turn that into the freeze out temperature of the dark matter. I can look at what the relic abundance would turn out to be. And then ultimately, I think the money plot is down here in the lower right. And what it shows is in the plane of the dark matter mass today at 0 temperature, and then the interaction strength MS, so remember larger MS is a smaller interaction, and therefore a larger final relic abundance. What we find is that for this range of masses, in the standard model, everything was excluded by xenon 1 ton. Xenon would have actually seen dark matter scattering with it if this had been the theory of nature. However, and that's because what I've done here with this line, the solid black line, adjusts the value of the interaction strength such that I get just the right amount of dark matter as a function of mass. However, if I do the same thing for freeze out during confinement, because the interactions are enhanced during confinement, I actually need a much smaller value of the interaction strength to get the right relic density for a given mass. And this actually means that I'm therefore moved away from what xenon 1 ton is excluded into a region where xenon 1 ton has some hope of seeing something in the near future, but we wouldn't have expected to see it now. And the red versus the black curves just show you what happens when I change the shift in the mass between positive and negative. The actual interaction annihilation cross-section doesn't depend on that shift, but then how I translate this into the actual mass itself does. And you can see the thresholds are also being shifted around as I do that. So then actually, sorry, I see now that there are some hands up. Would it make sense to take the questions now?
I think one question is for the first part, and second arised not so long ago. So I don't know, as you want.
Yeah, maybe I'll just say I paused, and if the questioners would like to ask their questions now, otherwise I'll just wait till the end.
No, I'll wait till the end. Thanks, Tim.
Okay, sure. Thanks, George. Great, thanks, Susan. All right, so then the last sort of application I have is for axion production. And so famously, the evolution of the axion field in the early universe is governed by when the temperature becomes close to the axion mass. And since the axion mass is proportional to the QCD scale, that obviously plays a huge role in what the axion abundance today is. So in a standard cosmology, I have an axion energy density that looks like this red dashed curve, which is labeled rho axion ST for standard. And you can see that there's a period of growth in the energy density as the mass is turning on, and then things get really interesting and freeze out when we sort of cross below that mass. If we imagine a universe where QCD confined at a much earlier time, the axion mass turns on at a very early time, and so the axion starts oscillating, which initially actually leads to a period of early matter domination. But then the axion density fades away, like matter does, until eventually we get back to the usual QCD scale at which things change, and there's a big jump, just because the mass is jumping, right? It's a non-relativistic particle. And at that point, we realize a much lower density. So there's a lot of actually interesting things that you can explore based on whether the axion mass turns on before or after the electric phase transition and so forth. We looked at a bunch of these in the paper here. But the point is basically that we get a different mapping from the axion decay constant, right? The thing that sets its interaction strength and also its mass and the relic density. And so what that means is that we can realize what is typically a suppression in the final density of axions. So what's shown here is the time at which QCD deconfines, meaning the time at which QCD goes back to normal is on the x-axis, and then the high scale value for QCD, right, the lambda at early times on the y-axis. And we plotted contours that show you how the axion density is adjusted in this cosmology compared to a standard cosmology. So in other words, how much do you deplete the axion density based on this early period of QCD? This pink square is actually the plot that I showed you before, where the evolution was on the previous slide. And there are two different values of F sub A shown on these plots. And you can see actually that you can realize depletion of axions that's sort of as big as around 10 to the minus 4 times the standard case. Or of course, if you make the enhancement of lambda small enough, or you make the deconfinement time early enough, it just looks like a standard cosmology again. So you can actually realize you can realize the correct density of axions for much larger values of the axion decay constant, and therefore much lighter axions than you would otherwise assume in a standard cosmology without any fine tuning. And so this opens up regions of axion parameter space, which otherwise would look very fine tuned. So I think I'm pretty much out of time. I just wanted to say one quick thing about the phenomenology of my scalar singlet phi, which is really, the interesting thing that's new and common to any scenario like this. So really what we're looking for is that singlet phi. It couples to gluons through a dimension 5 interaction, which is, again, was characterized by some scale. It also may mix with the Higgs boson of the standard model and therefore pick up a scaled down version of the Higgs interactions. In the parameter space that we liked, that realized the phase transitions that we wanted, it turned out that the mass of the phi was actually pretty low. It was around tens of GeV, and the mixing with the Higgs was also pretty small, around 10 to the minus 3. So that mixing is too small for the LHC to have seen a deviation in the properties of the Higgs boson that it's measuring, though it is actually large enough that something like a future linear collider could measure them that precisely. And of course, there could be, if there's dark matter, there could be some dark decay modes. So what this just shows is, as a function of the mass of that phi field, the singlet, the total decay width, including the channels into the partial decay widths into BB bar, taus, charm, and gluons, right, which are what are relevant in this mass range. And then also the branching ratios. And you can see that for the very smallest masses, decaying into gluons is basically all it can do. But the heavy quarks can also be very important, especially the bottom quarks if you're sort of just above the bottom quark, the BB bar threshold. And there were some work that was done on looking how to search for this kind of particle through gluon fusion if it's produced off shell. This was done by these authors. They actually managed to put an interesting bound on the parameter space that hadn't been seen before. But it turns out the region where we were living was just happened to be a little bit lower. So this is something that the LHC might be able to do and run through. Okay, so that brings me to the conclusion. So I've played with the idea that QCD may have undergone a period of confinement in the early universe. I think it's an interesting question. It highlights our general ignorance of the universe at times before BBN. I have to confess, I kind of came at this as how badly can I break the standard model and get away with it in the early universe? And I think the answer is you can pretty much break it pretty badly. But I think it's actually worthwhile to explore this as part of a general investigation into the possibility that physics may hold surprises at high temperatures of the early universe, even if maybe these high temperatures are still not very high, corresponding to very high energies. And then I highlighted a few applications of what you could do with a theory like this, like the baryon asymmetry, rescuing WIMP or axion dark matter, that otherwise would have been ruled out by direct searches. And I stayed very safely and consciously away from scales as low as Big Bang nucleosynthesis because of the potentially strong constraints. But actually, it would be a lot of fun to see how close one could skirt those bounds. And that would require actually looking more deeply into, much lower values of the confinement scale, maybe even changes to nuclear physics around BBN. And of course, very quickly, BBN is going to tell you you can't do anything. But I still think that understanding the boundary as to where things get constrained is very interesting. And of course, I see this as part of a larger program where we should strive to understand the space of what's possible in the early universe and what it might buy us and how we should be able to look for it using experiments we can build today. So thank you very much.
Thank you very much for the very interesting talk. And yes, we have some questions. I think George had a question.
Thank you, Tim. This was absolutely fascinating. Wonderful food for thought here. Can you go back to your slide that has the bubble nucleation at the confinement or chiral symmetry breaking scale? That one.
Like that one?
Yeah. So one question I put in the chat is kind of what is the latent heat? This is a first order phase transition now.
Right.
So you're nucleating by supercooling a little bit. And what is the latent heat here? Is that of order the Higgs Vev?
It is of order the Higgs Vev, that's right. Which in this particular case is the same order as everything else because kind of, everything is happening at the same time.
Okay, that's kind of what I thought. And so that's really interesting. So that looks like old models of what we used to play with first order phase transitions at the standard model QCD confinement or chiral symmetry breaking scale.
That's right.
So I mean, it's interesting. If there's enough latent heat, then you kind of suppress nucleation. And then
That's
the
right.
bubble walls will not grow by detonation at the speed of light. And so the phase transition actually takes much longer than a light crossing time. And that's interesting because fluctuations can grow at that stage. And you said this has nothing to do with neutrinos. Okay, now I'm going to contradict that. So neutrinos are everything here. So because neutrinos will damp out, neutrino diffusion will damp out fluctuations. Just wondered if you'd thought about that a little bit.
Not at all. Actually, I would love to talk about this more because that's actually an interesting application I hadn't thought of.
The other issue is what happens to those fluctuations, because this, the standard model QCD scale is extremely interesting from the standpoint of producing primordial black holes. Right. One of the reasons for that, of course, is the number of relativistic degrees of freedom drops by roughly a factor of 3 there, so the pressure goes down. So really, any fluctuation on that scale of the mass energy in the horizon at the QCD epoch gets amplified. So now you'll change that scale. So where you got one solar mass of mass energy in the horizon at standard model QCD, now you're going to have, a million times less. So you're going to have like 10 to the minus 7 solar masses in here, which is an extremely interesting scale from the standpoint of primordial black hole dark matter.
Wow. Yeah, I would love to follow this up. I'm following what you're saying, and but I hadn't thought about this at all, I have to confess.
Lots of fun. Thanks, Tim.
Thank you. There's also a question from Susan.
Okay, well, thanks. So I have a couple very brief questions. One concerns this consequences of the latent heat that would be implicit in this framework of a very early universe. And I'm mindful of talks by Gordon Kurczak and people like that talk about that large entropy injection in the early universe is actually severely constrained. It's some kind of maybe a flip of what George was just arguing about, neutrinos and damping of fluctuations and all this. So I guess I would ask in this scenario, if I have a very large latent heat in the early universe, where does the entropy go?
Yeah, no, that's a good question. It's not large compared to the existing ingredients of the universe, though, right? It's an order 1 change in the entropy compared to what's happening in the universe at the time. In other words, that's because everything's happening at the same temperature, roughly speaking. But I haven't actually given that a huge amount of thought, I have to say.
Okay, I just wanted to raise the issue. I mean,
no, it's interesting.
And then the separate question, I just find it very intriguing that we're going to make theta bar enormous at some early scale. Presumably, this picture looks very much like a standard model electroweak bendogenosis if we actually had a first order phase transition, but we would rely typically on delta Km to drive the result. And in your model,
right.
you're really using theta bar. And so one question, I've seen, this is maybe just a matter of asking about compatible speculation. But I will say that there's been discussion in the past of how we understand today simultaneously a very small theta bar, but yet a sizable delta Km. So the question in this scenario, do we explain, I mean, maybe we don't care, but how would we explain that particular outcome that we see in our universe today? I'm mindful that there are a number of people, I mean, Hiller Schmaltz, maybe some paper with Michael Dine, discussing different theorems that might always guarantee theta bar small. And then the universe evolves and delta Km can be big and theta bar can stay small. So how do we think about that today, given this kind of scenario? Or maybe
that is interesting. And unfortunately, I don't have anything to add to it, though. What you're pointing out is a very important point, that cosmologically, right, the fact that theta bar is large, if theta Km were dynamical, right, so theta bar is large because I've made it dynamical and allowed it to be. If theta Km is dynamical, then you could imagine that there might be some very interesting interplay, and it might be that, like you're suggesting, maybe it's actually a normal outcome that you end up with it all getting pushed into one and not the other, just by, say, the evolution of the universe, and not because of any, arbitrarily imposed UV dynamics. So that's actually a fascinating idea.
So that's a completely different. Okay, great. So very good. So, okay, a new direction, yet another.
Thank you. We also have a question from Lucas.
Yeah, hello, Tim. Thanks for the nice talk. My question is just brief. So since you have first order phase transition there now, did you think about gravitational wave signature?
We did, and we actually spent a lot of time with some collaborators, Juna Kroon, Shada Ipek, and Jessica Howard, actually trying to estimate the gravitational wave signatures. And the real problem is that the effective field theory we use, it sort of breaks down on both sides right at the actual phase transition itself. So, we have control over the weakly coupled quarks and gluons before confinement, and we have control over the mesons after confinement. But right when they're switching from one to the other, we can write down things like a Nambu-Jonah-Lacinio model, I mean, you can get actually answers, and the answer is that it looks like you should produce gravitational waves, but even then we just couldn't. It was so sensitive to the parameters, and we had so little control over them, that we felt like we didn't understand the answer at all, and so we never actually published our paper.
I see.
As a result of that. But it's a great question, and I really wish I had a better tool that I could use, because you need something that contains both the mesons and the quarks simultaneously. And so sort of by definition, this is a hand-wavy effective field theory. But of course, there are things like Jonah-Lacinio, which actually do try to do that interpolation for you. I just didn't actually trust that I understood the parameters in it well enough to know whether I could actually see the gravitational waves or not.
Right, I see. Thank you.
Okay, thank you. I don't see that we have any more questions. So Thank you, team, again for this very nice talk. And if I think we still have a few minutes if anyone wants to stay for the informal discussion.